Good afternoon, everyone. Just wanted to walk us through some of the general screening procedures that we discussed in lecture on Wednesday. Didn't get a chance to go over an applied example during class, so just want to walk through that through here. We're going to be using this SPSS screening, what do we call it? SPSS output screening handout that we have posted to the course website. Going to walk you through. This is going to be a nice template for sort of procedures moving through a general multivariate screening. In this case, we're just doing a basic screening, and so we don't necessarily have a specific model in mind necessarily for this. So our procedures will change a little bit when we jump into the regression stuff. It'll actually get a little bit more efficient in terms of looking for multivariate outliers and things like that. So, but we'll cross that bridge when we get there. Another thing too, aside from recognizing that this is a general screening, also wanting to recognize that this is for a continuous model. This isn't a group screening data. Remember that if we're doing group screening, what we need to go through, and so this would be things like ANOVA models, group-based stuff, we would need to go through and basically perform this procedure individually within each groups to make sure each one of our individual populations being represented in that analysis sort of are meeting our requirements for under the requirements of multivariate analyses. So the data that we'll use here is the Psych 5300 exercise screening data set. I'm just going to go through and save this right now as a scrap file, just so if I screw it up, I don't actually ruin the data set that we're going to be using. So again, would encourage you to do that always. So we've got that saved. Just as a descriptor of what we've got going on here, we have, again, a set drawn from people who have been exposed to motor vehicle accidents. And so here we've got all of our variables listed. We have PTSD diagnoses. This is a dichotomous variable, no, yes. Remember that for continuous models, as long as we have a dichotomous categorical variable that we've coded 0, 1, this is fine. We can include these in these models. Same thing as gender. We have that coded 0 for male, 1 for female. Age and years, obviously a continuous variable. We have racial ethnic identity. This isn't going to go into our model, but note that this is a categorical variable with multiple different levels. This is going to be a nominal variable, so we can't just stuff this into like a regression model. If we have something like this that we are wanting to include in a model, we're going to have to do some other stuff to make sure that we're either dichotomize this or doing some other types of coding procedures to go through and make sure that we can compare different types of racial ethnic populations in terms of our stuff. We're not going to use this here, but remember that anytime you have a categorical variable that has more than 2 levels, we're going to have to do some different coding before we can put it in our model. We can't just treat this as a continuous variable, 1, 2, 3, 4, etc. We have time since our accident. So this is when people come in, how long ago was the accident? We're going to use this in our model. Trauma history. This is a number of previous events that this person has experienced. Again, the idea being that if you have more adverse events occurring in your life, you may be more and more susceptible to different types of psychopathology. And then a PTSD total score ranging from 0 to 136, and a measure of perceived social support ranging from 0 to 7. Okay, so these are the variables that we're going to be looking at. Now, for this specific example, hypothetically, what we're looking at is basically screening for a regression analysis where we've regressed a continuous PTSD severity score onto participant age, gender, months since their accident, and prior trauma history. Okay, so these are the variables in the set. We're not going to use all of these. This is continuous, this is dichotomous, so that's fine. We can use that continuous, and this is a continuous variable, so we're good to go here. Okay, so Going to get started with the screening. As you're going through also, and if we scroll down to the bottom of this sheet, we have our final write-up that we've got going on under different headings. This is a nice template for you to take a look at and sort of start to use this to frame your own screening write-up. It doesn't have to be exactly like this, but sort of general information should be included in here. A couple of different ways you can do it. I like to have a notepad that I'm sort of jotting down notes as I work through. Maybe you want to type this into a Word document, but as we go through each one of these steps, it's nice to keep track of what you've done, what you've found, different things that have come up, so that by the time you work your way through the whole screening, you don't have to go back through and try and remember what cases came up as problematic, sort of what stuff were raised as issues and things along those lines. So I won't do that necessarily here, but just as a tip as you're going through and doing your own stuff, be sure as we're working through this to make sure to write things down. Okay, so here's our data set. Okay, first thing we want to do is go through and check basic accuracy and plausibility of our data entry. Okay, one good way to do this is to just go through and take a look at your descriptive statistics. So if we go to Analyze, Descriptive Statistics, and go to Descriptives, and in our variables, what we're going to include, we've got not PTSD diagnosis, but PTSD severity, right? That's our outcome. And then we're interested in age, participant gender, months since their accident, and social support. Oh, no, not social support, trauma history. Okay, here are all the variables in our model. If we go through and we select options and hit skew and kurtosis here and hit continue, what we can do now is go through and hit paste. This is going to open up our syntax file. Again, just like last semester, it's nice to have a file kind of like a template. It helps out in keeping track of what you're doing and why. Remember that anything that is preceded by an asterisk is a comment, and so you can type whatever you want here. Microphone's in my way. Here we might say accuracy and plausibility, just so you know what you're checking here. Okay, and so what we're going to do is we're going to go through and run this and take a look at our output. Okay, what we want to do at this stage of the game is just go through and take a look at whether or not all our values are within range. If we look at our ends, it looks like we're missing some data. We've got 390 people with all 1, 2, 3, 4, 5, all 5 variables, 390 with complete data, but as many in this sample as 458. So we've got a large sample, and this is going to help us with alleviate some concerns with some of our different potential violations. So this is one thing we've got in our bag. We've got a pretty big sample here. But right now, looking at just the minimum and maximum, making sure our values are within range. PTSD severity, if you look at your handout, for this measure ranges from a minimum of 0 to a maximum of 136. So it looks like we're good there. Age, 18 to 80, so we've got a wide range of people. That looks fine. Gender, 0, 1, no weird codings there. Months since the accident, 1 to 600. Huge range. Looks like we have at least one person in there who had an accident some time ago. And if it was a preview, we go through, look at our skew kurtosis, that's probably going to be problematic a little bit there. But we'll leave that for right now. And then number of traumatic events, 0 to 11. All that seems reasonable. We don't have any values that are falling outside the range at which we would expect as a real value, so we're doing okay right there. Okay, moving over and taking a look at some of our distributions. PTSD severity looks pretty good in terms of skew and kurtosis values. Again, best case scenario, we're looking for values that are less than 2. We've got a large sample here, so we've got a little more leniency. Here, gender, we're not going to look at distribution of that. That's a dichotomous variable, so that doesn't matter. But our months since our accident, looks like we have a pretty big skew and a massive kurtosis level. Even with a big sample, this is too much to try and say, oh, well, it's not a big deal. So months since accident is going to go down on our pad as a variable that's looking like it's going to be problematic. We'll have to probably do something with that. And then trauma history, number of traumatic events. The distribution on this looks okay as well. Now, one of the things to think about, and we're going to treat number of traumatic events as a continuous variable, but it's really not. It's a count variable. An account variable is an ordinal variable, and so if we're being very rigorous with this analysis, we might want to take a look and think about ways to treat this as a count variable. Now, we've got a range of 0 to 11. I mean, we can probably get away with treating this as continuous, but again, one of those things I want you guys thinking about is always what's the level of measurement, and then does that level of measurement map onto the types of analyses we're running. So based on this information here, we would say accuracy and plausibility looks like our values are within bounds and are reasonable. As we're sort of looking forward to our univariate distributions, it looks like we're going to have a problem with months since the accident. We're going to have to do something about that. But everything else looks pretty good here at this point. Okay, so push that down a little bit, and so taking note of that, next thing we want to do is we're going to go through, and it's important to remember this. So we've got a categorical variable in our model. We've got gender. Okay, now taking a look at our means, it looks like we've got 72% of our sample is women. Okay, basically our mean translates into a sort of percentage with a 0-1 categorical. So I already know that it looks like we have about close to 3/4 women to a quarter men, but always go through and want to take a look at your frequencies. So we've got gender as our categorical variable, and we'll paste that into our syntax file, run that, and we see, yep, 72% of our sample, 72.3. Of the total sample, whether we have data, looks like we've got one person who didn't report their gender, but 72.3% of the sample is women, 126 male. So this certainly isn't a balanced distribution, but it's not. Remember, we're talking about with reasonably large samples, we can tolerate a pretty decent imbalance in terms of the number of people we have. Here we have, say, 3 to 1. I mean, it's an imbalance, but it's not something that we're going to be too worried about. And so thinking about outliers with categorical variables, we're probably going to be okay here. We've at least got a reasonable breakdown. So we've gone through, taken a look, verified that our variables are all within reasonable bounds. But what we want to do now is we need to take into account addressing this missing data issue. Okay, we know from our output here that we have missing, that we don't have full data, and so we're going to have to probably eliminate those individuals that are missing some data. So a easy way, and we talked about this a little bit last time, but as we get into our regression models where we have more variables in the mix, one way to do this is we can go through and we can go compute, and we say missing equals, go through, highlight that, our variable list, and so we're going to say PTSD total plus age plus gender plus MVA, or months since accident, times trauma history, period at the end, exe, shortcut for execute. Okay, now what this is going to do is it's going to go through and create a variable called missing, and it's going to, we're doing is we're taking the additive sum of all of our variables, which isn't going to mean anything, but if we go through and we do this and we run it, what ends up happening is we've got our missing variable now, and if we sort this, any case that's missing any of the variables in our model isn't going to have a score here. Okay, with this sum statement here, and we can also go down, you could go down to transform compute variable, and if we were to go missing equals age plus gender plus month since accident plus PTSD severity plus, we got trauma history in there, trauma history, and if we were to hit paste, it says change existing variable. Here, let's cancel that, missing one, and paste that in. So you can do it through transform compute variable. It's, as you start to get more comfortable with this, it's often easier to just type that in, but you can do the same thing either way. But so what we're going to take a look at is we're going to go down through and we're going to say, all right, so we've got missing data on these variables, right? And so these are ultimately variables that we're not going to be included in our regression analyses, just because they're not going to be able to be estimated in there with the model that we're running. But what we want to do is we want to take account of this, right? So we want to say, note things like, it looks like we have 68 cases that have missing data, and if we go down through, take a look at sort of a good comprehensive write-up of this, not just saying that we have 68 cases with missing at least one value, but wanting to go through and indicate which cases are missing what variables to a reasonable extent. So it looks like if we go through, we've got age is missing. We've got one missing value for age, one for gender, one for months since accident. Looks like our majority of what we've got is missingness in that trauma history variable. If we look at trauma history, right, for whatever reason, we're missing a lot of scores here. Important to take stock of where your missing data are to try and give you a sense for what's going on. This is going to go back into thinking about mechanisms of missingness right now. So for these data, maybe we introduce this trauma history variable later on or something like that. Looks like age, gender, months since MVA, no missing PTSD total values. This is all probably just random stuff. This we would want to go through and go through our hard records and make sure that we knew why we were missing these. But important here to note that we do see a pattern in our missingness. It's mostly that we're missing data we're going to lose cases because we're missing values on this trauma history. And so always wanting in your own research to go through and make sure that you know, before you kick these cases out, wanting to know where they're missing data and why. Okay, and so then here we're saying this is what we've got for the reduced set. So going to go through on our missing variable, we're going to sort that, and then after we've reported and documented what these cases are and why they're missing, we're going to go through and nuke these. Okay, so all right, so we should have full data now, but always once you go through and modify your data set, want to go back through and take a look now and re-look at, not for accuracy and plausibility, but going through and taking a look at your full set now. Maybe we make a note here, say to ourselves, reduced set n equals 390, something like that, right? And what we want to do now, because this is going to be the set that we're working with at least to start out with, right? This is our set with full data. Want to go through and take another look at our descriptives and our frequencies just to make sure nothing crazy has gone on. So going down through, taking a look with our descriptives, we know that everything's in bounds, so we're not worried about that. But our distributions are all still within sort of reasonable range of what we would hope for, except months since accident. None of that changed, but we deleted 60-some cases. That could have a big impact on what your distributions look like. Here it didn't. That's kind of good for us, but always want to check. And again, it looks like our gender breakdown has stayed exactly the same. Okay, so this is nice. This makes me happy. It suggests that maybe that trauma history variable was missing more at random now that we don't have systematic fluctuations in these different variables. But so in terms of going through and taking a look at univariate distributions, first thing we're going to do is note that at least based on our skew and kurtosis values, all of our variables look okay except this month since accident. So we're probably going to have to do something there. Okay. So we've got, we know that months since accident is nasty, but what we want to do is also take a look at some graphical representations of what's going on here. And so what we're going to do is we're going to go down to descriptives, and we're going to use this nice little explore command. So we're going to go down and hit explore, and what we're going to do is start to load up the variables of interest for our model. So we've got age. We're not going to put gender in there because gender is a dichotomous variable. We're not interested in distributions on that. Months since accident, trauma history, and PTSD severity. Okay, so these are our variables that are going to go into our assessment here. Then the other thing you can do, you see down here, we've got this window that says label cases by. We're going to hit subject number and drop this down in here. What this is going to do is if we have weird outliers in our box and whisker plots or things along those lines, what it's going to do is it's going to label those cases based on the subject number for that case, as opposed to the case number in terms of what order it is happens to be with however we've got it sorted. So this is a useful thing to do. Make sure that you do this. This will help save you time in identifying which cases are weird outlier stuff. We're going to go plots here, and we're going to select histogram. I'm going to take off stem and leaf. I don't like stem and leaf. You can select it if you want, but I'm just trying to make this a little more efficient. Hit continue, and then we'll go ahead and paste that. Go ahead here, and we can say graphical, we'll say box plots and histograms. Okay. Go down through, hit our examine. Now examine, as you might remember from last semester, does a nice job. We go down through verifying that we have all 390 cases here, and then what it does is it just is going to go through, give some descriptive variables for each one of our, or descriptive statistics for each one of our variables. It gives us a lot of stuff that we don't get in the straight descriptives that can be kind of interesting. For instance, if you want to get a confidence interval around age, it does it there. We got trimmed means, mean, variance, standard deviation, min, max, interquartile range, skew, kurtosis, all this stuff. So this provides a lot of nice information. I just prefer the layout of the descriptive statistics. It's easier for me to see, but all of that. So none of this should be super new based on things that we've already done. But what we can go through and take a look at our distributions here. So age looks pretty distributed nicely, at least for applied data. We've got a couple people who are fairly old, right? And this is something that's set away from the rest of the distribution. I don't know that I would be terribly worried about that given the size of our sample. I don't think that these two individuals are going to draw off our mean too much, given that we have 390 people. But if I were describing what this histogram looks like, I would note that it looked relatively normal, but looks like we have a couple of older individuals hanging out there on the end. Okay, same thing if we look at our box and whisker plot. This looks wonderfully symmetric, with the exception of cases 284, 743, and 247. Looks like we have 3 people who are sort of reporting advanced age here at the end. So again, as I was talking about my distributions, would want to make a description of the histogram, the box plot, but then note that we have a handful of cases that are setting outside the distribution. Now, whether or not we're concerned about that, don't know yet, but I'm definitely going to jot those down on my list as people to keep an eye on. Okay. Months since accident. This was our variable with horrible skew, a skew of 4.57, kurtosis of 24, close to 28. That's why it's pretty easy to see what's going on here. Months since accident, we have most people right around, well, this isn't 0. This is probably about 3 months or so. But then we've got people stringing out into this really nasty distribution all the way out to 600 months. So again, we've got a clear skew with people jumping out. It's not a continuous distribution. Again, if we think about the type of variable we're looking at, this is months, right? This is amount of time, different than our sort of classic 0 to 5 scales where you can only be so far out on the end. Here, conceivably, for people who are older, they may have had an accident a long time ago, and this is where we start to get the types of distributions where we need to start taking some action to correct that before we jump it into our model. If we go down through and look at our box and whisker plot, that's a mess, right? All of this stuff going out. Whereas here, we've got 3 cases that are over 1.5 times the interquartile range from our 3rd quartile here. There's too many things to even try and address here, and it's just the kind of a horrible distribution, terribly skewed. So we're going to have to go through and do something with that. Okay, histogram of number of traumatic events. This is also skewed, but not as bad. Everything looks like a continuous distribution falling off into this tail. If we look at the box and whisker plot, we've got 1, 2, 3, 4, 5, 6 variables that are looking like they're larger, but again, given the large sample that we've got, 390, a continuous distribution, I'm not too terribly worried about number of traumatic events here. Okay, and then our histogram of PTSD severity. We've got a nice kind of normal shape. We've got looks like a couple of bimodal, trimodal things going on here. But again, overall, this isn't a distribution I'm worried about. Box and whisker plot look really nice here. Okay, so going through, taking a look at these, would want to, in your write-up, so we've got, make sure that you were talking about our univariate distributions. We've got skew, kurtosis values are acceptable. I like to put these in absolute value because you can have negative skew, positive skew, and if it's negative or positive more than 2, that's all bad, right? So we've got skew and kurtosis values acceptable for age, trauma history, and PTSD total, talking about describing what we're seeing in some of the graphs here, and then identifying skew and kurtosis, strong indication of violation of normality in our months since MVA, and then talking about kind of what we've got going on here in that graph. Okay, so, but to this stage we're sort of at a turning point. We've got a decision point. So 4 of our variables look all right, but this is not okay. This is clearly something we're going to have to do with now. And what we're probably going to want to do here is take a look and do something to address this distribution before we start going and taking a look at outliers, because it's ridiculous to ask if there are outliers in this distribution because we already know there are going to be outliers. So before we go into checking for univariate, multivariate outliers, we need to do something with this distribution because this is in clear violation of our assumptions. So what we're going to do, so we've got a strong positive skew, and if we go back through and take a look at our sort of range for months since accident, we've got 1 month to 600 months. What I'm looking at here is making sure we don't have 0 values. Now, given that I was part of data collection here, I knew that we're not going to collect anybody the day after they were in an accident. But remember that if we're going to start doing some of these transforms, we always have to go through and take a look, make sure that there's no zero values, because then that'll foul up our transform. So what I'm going to do is I'm going to go to transform, and I'm going to hit compute variable. And what I'm going to do is we're going to try a natural log transform to see if that starts to bring that skew in. So I'm going to call this variable ln natural log MVA months equals, all right, now if we go down here and we hit arithmetic, we find our SPSS has a loaded function for the natural log. So it's ln, go through months since accident. There we go. Okay. Down here you'll see a description of what these different features look like and what they do. So basically what I'm doing is I'm taking our months since accident variable, and I'm taking a natural log transform of this. And what I'm hoping is that natural log transform is going to bring that skew in a little bit better. Okay, so I'm going to hit paste. My syntax file. Okay, and again, I want to make a note. Say natural log transform given high skew in MVA months. Okay, just to remind yourself what you're doing and why. Go through, let's take a look here. Executed that appropriately. Take a look at our data set, and now here's our new variable. So this is the natural log transform of our months since our accident. Okay, and what I'm going to do now is I'm going to go down through and I'm going to say, all right, take a look at my descriptive statistics, because I want to see what my skew and kurtosis values are now for my transferred variable. Okay, so I'm going to hit paste, and I also want to look at descriptives, explore, throw those out because I already know what those are, but I want to look specifically at our natural log of months, paste that, and then if I go to my syntax file, go through and highlight this stuff to see what we've got going on. Okay, so going up and looking at the distribution of my the natural log transform of months since accident, this is much better. This is beautiful, right? This is excellent. This transform worked swimmingly, right? We went from a skew and kurtosis value of 4.5 and 14 or something ridiculous like that to everything less than 0.5. This was a successful transformation. This is kind of the best thing you can hope for. If we go down through and we take a look at our revised distribution, that looks much better than that, right? So this is a nice example of a variable that's maybe important in our model, right? But something that we can't just plug in given its raw distribution, because that's going to screw stuff up. That's a clear violation of our assumptions. Here we've used a natural log transform, which, as we'll talk about next week, retains some interpretive value, and so this is really kind of the best case scenario for me in terms of using a transform to address violations of normality in our data. Okay, so what we're going to do now is go down through and make sure in our write-up. So we've talked about problems here with normality in our months since MVA, talking about what that distribution looks like and why that's problematic. Here we're saying, well, what we did is we took a log transform, turned that approximately normal, histograms and box plot for the natural log is acceptable, we're good to go. Okay, univariate distributions, also make a note of our ratio of men to women in this sample, unbalanced but acceptable for dichotomous indicators, making sure that we've got our univariate distributions checked off our box. Okay, so next thing up is we're going to go through and take a look at outliers. So to go through and take a look at outliers in our data, what we can do is go back up and we can analyze, go to descriptives, and we'll kick this out, and we'll go age, gender, and we don't have to include gender, age, not months since accident, because we're going to be looking at the natural log, because we already know there are outliers in months since accident, trauma history, and PTSD severity. Okay, we've got, again, we don't need to worry about screening for univariate outliers in our dichotomous variable, because it can be 0, 1. We've already established that it's unbalanced but not terribly unbalanced, so we're fine. So we're just going to look at our 4 continuous variables here, including our natural log transform that we just created for months since accident, and then we're going to hit save as standardized variables. Okay, I'm going to paste that, and you'll see this looks the same thing as we saw up here, except we just have this save command. And what that's going to do is it's going to go through and it's going to save a z-score for each one of your variables. We run this, we go through, take a look, and here you'll see at the end z-score of age, of MVA, trauma history, and PTSD severity. Okay, and if we go to descriptive statistics again, I like to go through, kick that out, go through and just take a look at our z-scores. Don't standardize your standardized scores, because that'll give you z-scores on z-scores, which are the same thing, it just makes it clutters up your data set. And we'll go through and hit, if you want to, you can take off options. We don't need skew and kurtosis of that, because it'll just be the same as the raw variables. But okay, go ahead and hit paste there. And now what we can do is run descriptives on our z-scores. And what we can do here is start to take a look at where we have possible extreme values, right? So we've got a big data set. We've got 390 people. That makes us pretty robust to values that are kind of hanging out on the margins. And so I'm probably going to set my my threshold for values that I'm really going to start to be concerned about pretty high in terms of z-scores. For this case, I might set my criterion for what I'm going to call an outlier, a z-score equal to p, that would be associated with p value equal to 0.001, let's say. So that's going to be 3.29. So we're going to have, like, basically with this large sample, we're looking at values that are falling 3 1/3 standard deviations outside the mean. A little bit liberal, but I mean, it's a big sample. We expect to have some large extreme values in a large sample. Okay, so age, we're not worried about that. Remember, in the distribution, we have a couple people who look like they're in their 80s. They're sort of set away from the rest of the larger distribution, but at the end of the day, it looks like we're not going to be too concerned about those individuals. Our natural log transform of months since the accident is looking pretty good, right? So our transform was effective there. Number of events in terms of trauma history, we do have, it looks like, some high values here. So we're probably going to want to go through, take a look at that. And PTSD severity, again, that's looking reasonable. Nothing that would suggest any problematic outliers there. Again, if we go through, it looks like the only variable we're having some potential difficulties in, or we want to look into further, is number of traumatic events, right? And so if we go back up just to remind ourselves what that looks like, it's this distribution. So it looks like we probably have a couple of these cases that are registering as univariate outliers, or variables with standard score larger than 3.3, 3.29. So want to go through and let's take a look and see which cases those are. So if I go to my data set and I go to my trauma history, my z-score for my trauma history, sort that ascending, what I can do is I can go down and find out where are my offenders. Okay, looks like I've got 3 cases. So we've got 3 cases that are reporting pretty high levels, or a pretty extensive trauma history, right? So it looks like it's cases 7, 137, and 166. And if I go and I look at the trauma history variable here, so these people are reporting 10 and 11 prior probable traumas. Okay, so my question is, what do I do with these people? Okay, these are clearly extreme scores within this distribution. These are scores that are lying over 3 standard deviations beyond the mean. So my question is, what do I do with these people now? So some options, right? We had talked about removing them. Are these people a part of our intended population? My answer would be yes, right? Again, we've got a big sample, and it's probable in a sample of close to 400 people, we're going to get a couple people that have just had really tough lives. There's just been a lot of stuff. They've been through a lot of stuff. I wouldn't necessarily want to throw these people out. They're not part of the population of interest, and so I think throwing these people out is probably not an option, or at least wouldn't be for me. We also talked about smoothing procedures, but really, I don't know how we're going to smooth this, because again, these are all part of a continuous distribution. Our outliers are sort of the next highest levels. They're just these last ones here on the end. It's not like, say here, if we wanted to smooth these cases, which we don't need to, but if we wanted to, we could say, all right, these people, we're going to sort of assign them a value, an age, sort of 1 unit higher than this. If we want to do a smoothing procedure, again, we wouldn't do that because we don't need to. But here, this also isn't going to be effective because they're already smoothed, right? And if we eliminated these, if we deleted them, probably what's going to happen is these cases here are just going to start registering as high extreme values. So in considering my options, I'm probably going to note these cases, but not actually do anything about them. 1, they're part of my intended population. 2, these are people who are a part of the continuous distribution in terms of overall trauma history. And 3, I've got a big sample. They're going to be large values, but probably not large enough to go through and make an appreciable difference in a sample of 390 individuals, right? Their scores are 10, 11, not 20 and 25. So what I'm going to do probably with this in my screen, I'm going to note these as extreme values, but I'm probably going to leave them alone and not do anything with them. Okay, and so again, if we go down through, take a look at what we're doing with our univariate outliers, say no univariate outliers, identifying sort of what we're calling univariate outliers for these variables. We're saying all of our z-scores are less than 3.17. 3 cases as extreme, trauma history scores, case 166, score of 11, corresponding z-score. This case, score, z-score. This case, x z-score. And then a justification for what we did. We say no efforts to alter or remove, given that potential extreme values represent a smooth continuation of overall. Note the boundary values expected in a large clinical sample. And so we're going to say, yep, they're there, but they're probably not going to be as big of a concern as would be for maybe a different variable. Okay. So we've got our univariate outliers taken care of, right? Next thing we want to do is start to go through and try and identify multivariate outliers. Okay, multivariate outliers. Little trick that we can use. Tabachnik and Fidel talk about this. What we're going to do is we're going to go through and we're going to go and select linear regression. And what we're going to do in this linear regression is we're going to go through and we're going to include our variables. So we've got age, gender, months, natural log of months since accident, trauma history, and PTSD severity. Okay, so these are all the variables in our model, right? But what we're going to do is we're going to regress all of these variables onto some arbitrary variable. Here, it's just going to be our subject number. Okay, so this regression model doesn't make any sense. Subject number is assigned sort of however people come in. So this isn't an interpretable value. But what this is going to do is it's going to go through and it's going to take a look at the relations of our variables of interest within multivariate space. And what we can do is we can start to get indices of multivariate collinearity, of multivariate outliers. And so this is a nice procedure for going through and detecting some of those hiccups, potential hiccups in your data. So what we're going to do, statistics, going to go through and we're going to ask for collinearity diagnostics. Okay, this is going to tell us among our variables how closely are they associated. This is going to give us some of those tolerance values that we had talked about in class. So for this, we're going to hit continue. Plots, we're not going to worry about that. Under save, we're going to click Mulholland-Ovis distances. Okay, we can also select Cooks, I guess, if we want to. But what we're doing here is going through. These are going to be our metrics of multivariate outliers, right? And so we're going to go through. Collect those. This is just going to save these a value for each one of our cases as a new variable in the data set. So we're going to hit continue here. And then let's go up to statistics. We can do case-wise diagnostics. This is less useful for what we're doing here, but we can do that anyway. And then we're going to go ahead and hit paste. All right. So this is our regression model that we're going to use to evaluate multivariate outliers and multivariate collinearity. Okay. So you can go through, run this regression model. And so the model itself isn't interpretable, although you will note that we have a significant model with an R-squared. The combination of our variables accounts for 2% of the variability, or 3% of the variability in subject number. So again, I think a nonsensical model, but I think a nice way to recognize sort of the limits of statistical significance, particularly with a large sample. Basically, we're saying that the combination of PTSD severity, age, gender, natural log of months since accident, and trauma history predicts subject number, right? This is just random noise, but something that's worth noting in here. Okay, so we're going to ignore this. First thing, though, that we're going to go through and take a look at, because a couple of things we're getting from this. First thing is an index of multivariate collinearity, right? So we can go through and take a look at these tolerance levels, right? And remember, tolerance is 1 minus the squared multiple correlation of our variable regressed onto all other variables. So if we take age in years and regress age in years on everything else here and get an R-squared value for that regression model, this tolerance value is 1 minus sort of that. Okay, technically, we were talking about sort of having concerns with tolerance values that are very low, around 0.1. We're going to start to become very concerned far before we get to a value that low. But if we look at our tolerance values here, these are all 0.9 and above. No evidence of problems with collinearity within these variables here. Again, remember with tolerance, we're looking for very low values. These all high, these ranging tolerance values ranging from 0 to 1, so we're good. So we can go through on our screening checklist and say that we've got no problems with multivariate collinearity based on assessment or review of our tolerance values here. We've got some other collinearity diagnostics. We can go through and take a look at those, or we'll get into those when we get into a specific screening for regression. Don't worry about those for right yet. Same thing with case-wise diagnostics. We'll look at those when we get into actual real regression models. Won't worry about it for here. But the one thing we do want to take a look at down here in our residual statistics is our Multivariate distance. Okay, remember your Multivariate distance is a sort of a measurement of the distance in multivariate space of the combination of your individual cases and their predictors from the centroid of the overall model. The centroid being the sort of the convergence of all means of all your variables in multivariate space, and then how far away any individual case is from that centroid. Recall that when we're talking about Multivariate distance distributed roughly on a chi-square distribution with degrees of freedom equal to the number of variables in your model. Okay, here we've got, well, technically we have 6 if we include subject number. I'm not going to. I'm going to say we have 5 reasonable values in our model. And so if we take a look at a critical value for a chi-square distribution for 5 degrees of freedom at p equal 0.001, we get a critical value of 20.51. Okay, and so what that would suggest is that would be the critical cutoff for identifying a multivariate outlier in our data, is a case having a Multivariate distance that was greater than 20.51. And if we go through and look at our Multivariate distances here, we do see that we've got a case with a Multivariate distance of 22.7. So looks like we've got someone in our data set that's sort of atypical. Okay, so what we've got to do is we want to go through and make a note of that, and then what we want to do is we want to see why. So if we go to Multivariate distance, you'll see in our data, right, that we've got a value for SPSS has created a new variable for our Multivariate distance that's created a value for all of our individuals. If we go through and we sort this and go down to the bottom, we can see that case number 166 is our case that's registering as a potential multivariate outlier in this data set. Okay. Now, if you're thinking about this and have been keeping track of stuff, case 166 has already come up in in a previous screening, right? If you remember when we were looking at univariate outliers, 166 was the person in our sample that's reported a high trauma history. And so this is one of the things that will happen as you're going through and running these screenings. You'll see the same bad penny come up again and again and again and again. It starts to become a good rationale. If you're seeing violations across multiple domains and it keeps ending up being the same person, maybe someone who you might want to go through and think about excluding. Okay, but so it looks like probably, if I had to guess, probably one of the things that's causing this individual to contribute as multivariate outlier is probably this trauma history variable. But what we always want to do is go through and sort of make sure that we have a good sense for statistically what's causing this to be a multivariate outlier. Okay, so what I'm going to do is I'm going to go data or transform compute variable. I'm going to say create a variable called MV1. This is our multivariate outlier 1, and we're going to set, 0. I'm going to hit OK. So what we're going to do when we're trying to identify, so we've identified that we do have a multivariate outlier, and let's say, well, this isn't, but let's say that case, so here we've got a Multivariate distance of 19.5. Our cut point was 20.51. This isn't a multivariate outlier. I'm just going to do this just to demonstrate how you would go through if you had multiple multivariate outliers in your data set. So maybe we're saying 54 is potentially a multivariate outlier because we're setting our critical value at 0.01 instead of 0.001. What I'm going to do is I'm going to go through and I'm going to create a second multivariate outlier of 0. Okay. So what I've done is I've created 2 new variables. Okay, and what I'm going to do is I've set these variables all equal to 0, right? So everybody has a 0 value except for this person. Okay, case number 166 gets assigned a value of 1, and then we're going to do the same thing. Case 54 also gets assigned a value of 1 here. Okay, so basically what we're doing is we've got an indicator variable that indicates which case is the case that is being assigned as a multivariate outlier, and we're going to have the same number of variables as the number of multivariate outliers we've identified in the set. Okay, so what we're going to do now is we're going to go down through, and we are going to go to Analyze, Regression, Linear. Okay, and now instead of subject number, what we're going to do is we're going to take this indicator variable, MV1, and we're going to make this our dependent variable, and we're going to have all of our predictors predicting the 0, 1 variable here. Okay, this is not a reasonable analysis that you would ever run, but it serves a purpose, and Tobachik and Fidel go through this procedure. We're basically hijacking a regression analysis to try and get a sense for what variables are causing this one case to be a multivariate outlier. So statistics, I'm going to turn off collinearity and stuff like that because that's just going to muddy up our waters. Save, I don't need to save Cooks or Mulholland's distance here. Okay, and the rest of that's fine. Okay, so I'm going to hit paste. And then my syntax file, so we're going to sort of say looking for variables causing case number 166 to register as multivariate outlier. Okay? Because we never just want to say, oh, yep, there's a multivariate outlier, and then be done with it. We always want to say why, or be able to determine what specifically about this case is causing it to be odd in multivariate space. So we're going to hit run, and what we've got here is we're just going to go through and we're going to take a look at which variables end up being significant predictors. Okay, so here we're seeing 2 of these. We're seeing trauma history, number of traumatic events, is sort of registering as a significant predictor of this case. We guessed that because this was the only case that this was a case that already registered as having the most extreme number of events in the model. But then we also say PTSD severity as another predictor. So the combination of number of events and PTSD severity together are probably what's causing this case to register as a multivariate outlier. So if we go back to our data, okay, and we take a look at this case here, we already know that they've got trauma history is high. It's the highest in the entire set. So we already had suspected that. But then if we look at our PTSD total, okay, we've got a situation here where we've got someone who's experienced or is reporting 11 unique traumatic events, highest in the set, but then they have a PTSD score of 2, right? Remember that our PTSD score ranges from 0 to 136. With this type of trauma load, what the model is probably doing is expecting this person to have a whole lot more symptoms than a score of 2. Basically 0 scores, basically no scores, right? And so what's going on is not only is this case have a high level of high trauma history, it's got relatively no PTSD symptoms, right? So the combination of high trauma history and combined with virtually 0 severity is what's causing this case to be a multivariate outlier. Okay, and so what we would want to do in our write-up is we would go through and say case number 166 identified as a multivariate outlier, given the value based on critical threshold chi-squared of 5 of 20.5. High value for prior trauma history combined with low levels of current symptoms define the case as a multivariate outlier. Participant removed from the final set no further evidence of multivariate outliers. And so basically what we would do, it looks like we're going to go through and eliminate this case, because multivariate outliers are weird. They don't generalize to the overall solution very well, and we're probably going to go through and just eliminate multivariate outliers. Okay. Now the other thing we could do, just as a demonstration, case number 54 didn't register as a multivariate outlier, but we could go through just to show you how we would do this if we had multiple cases that we flagged as possible multivariate outliers. So we're going to go regression, linear. Instead of predicting that case, we're going to predict this case, and OK. And here we've got a similar situation. High number of prior trauma and what looks like low PTSD severity. Okay, so if we go through, take a look. So here, 9 traumatic events, and again, very, very low trauma history. So again, what we would do is for every case that we identified as a possible multivariate outlier, would have a dummy code that identifies that code versus the rest of it and regress everything on there. In this case, we're not going to be worried about case number 54. It was close to being near our threshold, but didn't quite get there. But 166, this is a clear multivariate outlier. We generally will delete multivariate outliers after we've identified what makes them multivariate outliers. And so what we're going to do is eliminate that case, make sure that we document it here, say why we've eliminated it, and then what we're going to do is we can go back through, we get rid of these variables here, and go back to our syntax. And now we're going to rerun things just to make sure that we don't have anything else. Once we've eliminated that there's nothing else that's going to pop up. So if we go through and run through, eliminate, or after we've gone through, so we've got a smaller set, we've got 389, but we go through, obviously we're not worried about changes or multicollinearity. The removal of one person isn't going to change that at all. But if we go down through and we take a look at our Mulholland Obis distances, highest one that we have now, 19.9. This is below our cut hole threshold of 20.51, and so we're going to say in our write-up that we've got, we removed that participant 166 and then reran. Looks like there's no further evidence of multivariate outliers in our data. Okay. So again, we were willing to tolerate case 166 when it was just a univariate outlier, but it also looks like it's contributing as a multivariate outlier, so we want to go through and get rid of that. Okay. Next thing we want to take a look at is our concerns with making sure that we don't have linearity or problems with homoscedasticity types of stuff. And so what we're going to do, remember, in terms of linearity, homoscedasticity, we're going to be evaluating our data using some graphical methods. So we're going to go through graphs, go to chart builder. And we'll go down through and we're going to hit scatter dot plot. Now, we've got 5 variables, 4, I guess, because it doesn't make sense to look at, well, yeah, I guess it does. We could look at, do we look at, yeah, probably don't need to worry too much about distributions of our dichotomous variables. We won't worry about here. What we'll go through and do is we're going to go through and take a look. We want to look at the correlations between all of our continuous variables in this data set, right? Because what we want to make sure that we don't have is any nonlinear relations, and that our linear relations are reasonably homoscedastic. Okay. Again, we're not looking for or what we're looking is hopefully no fan patterns and things along those lines. So we're going to go down through and so click scatter dot, and then you're going to hit this matrix, pull that up, and then all we need to do is we need to take our continuous variables. So we've got age, not months since accident. We're going to have natural log of months since accident. We're going to have trauma history and PTSD severity. Okay, we're going to just drag all those down into our plot, and then we're going to go through and hit paste. Here, chart builder, we'll say looking at linearity and homoscedasticity. Okay, so go down through and we're going to run this, and it's going to give us something that isn't terribly useful. Okay, this is kind of a mess. There's not a whole lot we can tell from this, but what we can do is start to adjust this and do a couple of things to make some of these relations a little more clear here. So what we want to do is double click on your chart here. Okay, and it's going to bring up an editor. What you want to do first is double click on the border of this matrix right here, and it's going to bring up a little tab. And so what we're going to do is start, and this is just dimensions that I figured out have been useful at least. Change your height to 550 and then hit apply. This will change automatically. Okay, it's going to blow this up, make this a little bit larger. Okay, so it makes it larger. I can see a little bit better, but it's still not great. These dots are pretty big. And so what I'm going to do is I'm going to go through and I'm going to click on one of these dots, and it's going to bring up an option to start changing these. And what I'm going to do is I'm going to change this to something that I like better. It's going to make those dots smaller. I'm going to turn the fill red with the border black. I like that. I'm going to hit apply. Okay, and it's going to give us a better sense for individual points in this stuff. Okay, so I'm going to close out of this now, and I'm going to do a couple other things just to take a look. I'm going to choose elements, and I'm going to say fit line at total, and make sure that we've got a linear. We could choose other types of trend lines here, but we'll just go with linear because that's our assumption. And we'll hit close there. And then options. This is kind of slick. Go ahead and hit show charts in the diagonal. And what this will do is this just puts together a nice plot where we've got bivariate scatter plots in the diagonals, your histograms, in the off diagonals, histograms in the diagonals, and go through. And that just gives us a little bit better graph to go through and take a look and start to make some assessments on linearity and homoscedasticity. Okay, so again, first thing, linearity. What we're looking for here is any clearly nonlinear plots, right? Are there in this scatter plot any evidence of clearly nonlinear relations? And I'm not seeing anything here that I would necessarily say, oh yes, there's a clear nonlinear relation going on here. So go through and sort of very simply say sort of linearity doesn't look like it's going to be a problem. But in terms of homoscedasticity, remember homoscedasticity says that sort of the variability for y at each value of x is about the same or vice versa, right? So if we're looking at this, what we're looking for is cases where we might have sort of something that looks like a fan pattern or unequal distribution in our outcome across different levels here. And so I'm not seeing anything that's too terribly bad, although maybe something like this, right? So here at the low end, so we're looking here at the relation between number of traumatic events and age, right? So number of traumatic events here gets increasing from none to a lot, age from very young to older, and it looks like we might have a problem with heteroscedasticity here. It looks like we have less and less variability in age as the number of traumatic events increases, which kind of makes sense, right? For people who are only 18, you've only been around for so long for things to happen. But as you start to get older, or more and more different traumatic events, we see less variability in age, probably because we're talking about adults and things. Now, it's difficult to get a good sense for whether or not we've got a problem here, but I might sort of eyeball this as a possible follow-up set to take a look at. Other thing too is it's involving trauma history. Remember that we can get heteroskedasticity as a consequence of nonlinear or non-normality in our variables. This variable, our number of trauma events, has the most skew of any of our data, and so maybe we might want to go through and follow up with that. We're also seeing what might look like a decreasing pattern of variability with respect to the relation between PTSD severity and natural log of months since accident. As PTSD severity increases, maybe seeing a slight decrease in the variability in sort of time since the accident, or the natural log of time since accident. It's kind of tough to tell, but again, what we want to go through is take a look, and what we're looking at in terms of heteroskedasticity is a difference of about a 3-to-1 pattern in the variability at the smallest versus the largest point of the scale. So everything else here, I mean, looks like not too bad. We've got a couple of things out here, but these are just a couple of random points. What we're looking for is systematic differences in variability. So maybe what I'm going to do with my follow-up, so this is a good graph to give me a sense for overall what's going on, but then want to follow up with maybe these two variables, right? So first thing I'm going to do is I'm going to look at the relation between trauma history, number of events, and age. So if I go graphs, chart builder, and I go to my scatter and I just do my regular, right? And I go trauma history, number of traumatic events, age in years, here, and hit OK. All right. Blowing this up, it looks like less of a concern. Here we've got only a couple data points, but if we look at the variability here, looks like sort of 25 to 60, right? So 35, and here we've got sort of 20 to 80, 60. So not a spread or a reduction in variability that would sort of be a 3-to-1 at the largest to the smallest. So on closer evaluation, it looks like we probably don't have any problems with heteroskedasticity there. Other one we wanted to take a look at was PTSD severity and the natural log of months since the accident. So we go here, and we'll say, pull this out. So PTSD severity here, pull this out, and months since the accident. Okay. Oh, yuck. Oh, whoops. That's months since the accident, not natural log of months since the accident. This will get better when we get the right variable in here. So that's out, and then we're going to go natural log of months since accident. Okay, much better. This is this is why we transform this variable. But again, if we look at here, sort of the high end of PTSD severity, we've got a range of say 0 to 3, and it's 0 to 6. I mean, we've got a 2-to-1 difference, something here. So again, not anything that we'd be concerned about in terms of a clear violation of our assumptions. Okay, so again, going through and taking a look, linearity, no obvious nonlinear relations in the scatter plot of age, natural log, blah, blah, blah. Variance assumptions, initial review suggests possible violation of homoscedasticity in trauma history and age, and PTSD total natural log of months, but individual scatter plots not demonstrating anything, a spread exceeding a 3-to-1 ratio. Okay. Other thing we want to take a look at is multiclinearity. Now we've already gone through and taken a look at tolerance levels, if you recall, up here, and said that we have no problems in terms of and we did this when we were screening our multivariate outliers, no problems with collinearity in terms of multivariate space. Last thing we would probably want to do is go down through and run some bivariate correlates where we would look at age, gender, natural log of months since accident, trauma history, and PTSD in terms of our bivariate correlations. Your outcome. Writing bivariate correlations for linearity. Okay, go through and run these. All right. So just looking for incredibly high correlations, and there's these are surprising. These variables are surprisingly unrelated to one another, which may not mean good things for a model. We've got, looks like months since the accident has a negative or natural log of months since accident has a negative correlation with PTSD severity, and then positive, a very slight positive relation between number of traumatic events and PTSD severity, but in general, nothing here that would suggest a clear difficulty with collinearity issues, right? And again, sort of the relative independence of the variables in our model. Again, seen very clearly in our very high tolerance levels. High tolerance levels are good, suggesting that you don't have a whole lot of overlap in terms of your variables in your model. Again, rule of thumb, tolerance levels around 0.1, but again, you should be very concerned about things that even get close to, that would even start to get in sniffing distance of any of that stuff, right? Would suggest redundancy in sort of the variables that you've got in your model. So go through in our outcome, say multicollinearity, bivariate correlations all within acceptable range, from negative 2.31 to 2.02. Tolerance values greater than or equal to 1.9 or 0.915. We'll talk about VIF. You don't have to worry about VIF necessarily right now. But so no evidence of multivariate collinearity. Okay. So this is the final write-up, right? So we're going through and saying accuracy, plausibility, missing values, total number. Now, if you've got missing values scattered all over the place, you don't have to list values for every single one. But in this case, we had pretty complete data with the exception of trauma history, so we're just kind of sort of giving a sense for where those were. Cases removed, 390 for the reduced set. Skew kurtosis, talking about the histograms going on there. Skew kurtosis for our, and sort of talking about these as a group because these all look pretty good. Skew kurtosis for months since accident is problematic. Talk about what those graphs look like, what we did to change that. Talking about distribution of our categorical variable here. Talking about our univariate outliers. Saying we're good, sort of we're indicating what our threshold is, what we're using to identify outliers. Say they're good for these three. All our Z scores for the combination of these are less than or equal to 3.17. We did find stuff that's coming up in trauma history, identifying what the cases are, what the value on the variable was, and what the corresponding Z score was. At this point, we're saying we're not doing anything with that because smooth continuation of the distribution. We expect some boundary values in a large sample. However, when we get down to multivariate outliers, this case 166 also came up as a multivariate outlier going through based on our criteria. Mulholland-Novus distance scores here. Go through and determining why this is a multivariate outlier. Huge trauma history load accompanied with a very, very basically zero severity here. Multivariate outliers, we're almost always going to exclude those from the set just because they do funky stuff. So we kick that out, and so we've got a final set of 398. Going through talking about our linearity assumptions, our variate assumptions, assessing multicollinearity, and then going through and providing a recommendation saying this is what we found, this is the potential problems, this is what's going on. So data with final set reasonably assumed approximate multivariate normality, barring potential biases as a result of non-random missingness in trauma history variable, right? Because we don't know why that was missing, right? But assuming that that's not an issue, data otherwise suitable for multivariate analyses. Okay, so that was a pretty long and extensive run through of this screening process, but hopefully that goes through and is helpful. Gives you a sense for the types of things, considerations, stuff that you're going to be looking at. Again, we'll change things a little bit when we get into screening specifically for regression. There's a couple of spots in that will make it a little bit more efficient than what we've done here. But in terms of screening of continuous data, this is kind of what we've got going on. Now remember, with grouped data, we sort of basically have to split our file by our grouping variable and just do this individually for each group. But hopefully this gives you a sense for general procedures, things along those lines. But if you have questions, make sure to come ask me, let me know, shoot me an email, and hopefully this was helpful. Okay, good luck. Hope you're having a good weekend, and we'll talk to you guys soon.